Hello. Today's lecture is a pre-module. In this lecture, we can mainly deal with the pre-object. We have already known the concept pre-Abelian group, and via pre-R module, and the general concept of the pre-object. Before to deal with the concept, we will deal with some concept of the R module, about the concept submodule and cyclic submodule and R module homomorphism. We will introduce some concepts of R module by comparing the group or ring that we have already learned. This concept, we can say these concepts are analogous to the concepts of group or ring. For example, we can deal with, before we can the concept of the submodule, we can discuss with the subgroup. The definition of a subgroup is here. If G is a group, G star, the operation is well defined. G star is a group. Then consider the subset of G. Definition of a subgroup is the subset H is a group. But to define H is the group, some conditions are required. Firstly, H star rather than the star is induced operator in H. So because of the H is also group but obey the G, this operator is inherited or induced in H. So H star is well defined. Second, identity. If identity is in G, since G is group, apparently identity is exist, but this identity is also inherited or induced. And the third condition is the existence of inverse. If three conditions are satisfied, then H is subgroup of G, which is denoted this symbol. So it means the subgroup, and with the same sense we can define even if we not write the definition. However, we can define subring. This means if group ring is given, then subset of S, for example, S is also ring induced operation, which is induced operation in R. So, in some sense, we can define similarly. Not the condition is not the same, but we can discuss similarly concept of the submodule. So the concept is the definition of the submodule is here. Let R be a ring, and A is a R module, and B is non-empty subset of A. And so this subset concept, we wish the subset B is a submodule, but obeyed in the set R module A. The definition of R module is, since A is an R module, so we can consider R A to A, and we can think the definition of the R module, but here B, and we can derive R product B to B, and we will want B is a role of R module. To do this, the definition of B is submodule of A, provided that if B is an additive subgroup of A. In this concept, the condition are satisfied. So here, and the condition RB, okay, choose two element product RB and goes to the RB, but this is the B, any element in R. Then we can say B is a submodule of A. Now let's talk about cyclic module over cyclic submodule. As earlier I referred, this is also analogous concept of group, and particular we learned the concept of cyclic subgroup, a cyclic group. What is the cyclic group? Cyclic means turned back. So the rough definition of the cyclic group, if let G is a group, then if some element G such that A is generated or group Z, then G is a cyclic group. And but some element does not generated whole group, but this can be a subgroup of Z. So this say is cyclic subgroup. For example, consider G12. This is a clearly cyclic group. Some element, for example, 1 is the identity of additive. This is clearly generated. Of course, we can pick the element which is generated the G12. This is the related if the GCD, if this is relative prime, so For example, if we choose 5, we can generate 12 because the theorism 5 and 12 is relatively prime. If we element relatively prime element, we can generate the whole set, whole group. But if we choose 2, this is does not generate 12 because this set does not contain the odd numbers. But this is also cyclic subgroup, and this is cyclic group. So G11, 12 is cyclic group. In some sense, analogously, we can discuss the existence of cyclic submodule or cyclic submodule. The definition is here. Let X be a subset of module A over a ring R. In this case, X A and A is R module. This means R A to A is characteristic is not so bad. This is condition. We know the 3 conditions. Okay. If X consists of single element, in this case also same, single element. If X is single element A, then the submodule generated by X is called the cyclic module generated by A. This singleton set is generated. A singleton set is generated X. Or if singleton set is generated A, then this is cyclic module. If some element is generated X, then cyclic submodule. Is analogously the concept of the cyclic group. Now let's discuss with the R module homomorphism. Similarly, we can start with familiar concept, group or ring. In this case, ring is good concept to understand. And homomorphism is roughly saying operation is preserved when ring transform into another ring. So to define the homomorphism, to discuss the homomorphism, there exists 2 rings. In case of ring, 2 sets exist. So let RS be a ring. In this case, the operation is well defined. So in ring R, the operation is here, and ring S, this operation is defined. Even if the symbol is the same, but the operation is thoroughly different. We can catch the concept. We must catch this concept. Then we can say R is homomorphic. Homeo is the concept of topology. R is homomorphic to S, but I'm a little confused when I'm using the word. homeomorphic to S means there exists a function f r to S. This function describe the operation is preserved. So A1, A2, of course A1, A2 in R by A1 plus this operation is changed by A2. Then R is homeomorphic to S, and this map is called homomorphic to S. This map is homomorphism. Homomorphism. The most important thing, one of the most important concept, rule, the homomorphism is we can analyze the factoring. So if R is given, factorize the ring. So there exists the representative member, even the another member exists, but there in factoring the representative element is represent literally all of the element. So what is this factoring is similar isomorphic to another ring. So isomorphic theorism can observe what is the factoring is isomorphic to another ring. So if R is given, then factorize the ring, and if we can find homomorphic R is homomorphic to S and natural function is given, then the isomorphic theorism R over I is isomorphic to S. So the isomorphic theorism under the concept of the homomorphism gives the another good idea to analyze factoring. Similarly, we can define the R module homomorphism. This concept is similar to ring homomorphism. So the definition is here. Let A and B the modules of a ring R. Two set, in this case a ring, this is modules of a ring R. So a function f A to B is called R module homomorphism satisfied if the two conditions are satisfied. This means the operation is preserved by F, similarly to the ring homomorphism or the group homomorphism. And if we're using this concept, we can also construct or analyze the factor sense. In this case, because A and B are additive group, why? We can, previous time, we can define R. When R module is defined, the A is additive group. So if we using this, A is given, then the factor, in this case factor group or quotient group. Also the quotient ring is okay. So this, if the given the submodule I is given, then factorize the module, then if A and B are R module homomorphism, then A over I is isomorphic to B. So this map, from this map, we can analyze the factor vector group, the representative is isomorphic to B. This main slide in this lecture. The concept is pre-R module. Of course, before we discuss the pre-R module, I will discuss with the pre-Abelian group, which is similar concept to pre-R module, similar structure, pre-R module. Let's see the pre-Abelian group first. This first statement is taking a following equivalent. So every statement is equivalent statement. Then, it's here, this is here. Then, F is called pre-Abelian group if the condition is satisfied. First, F has non-empty basis. What? This is non-empty basis? Second is F is the direct sum of infinite cyclic subgroups. Before to the discussion statement, we said this here. Cyclic group is cyclic subgroup, but infinite cyclic subgroup. What this means? Note that if G is cyclic group, then every cyclic group classified as two groups. First is G, second is Gn. So if the cyclic group is given, G is isomorphic to integer or Gn. Every cyclic group is classified as 2. This depends. What is depends G or Gn? This is by order. So if the cyclic group is order, this notation is order of the group is finite, then this is isomorphic to integer. This infinite. This is isomorphic to integer. And otherwise, if the element is finite, then the cyclic group is classified into Gn. So this statement B from this infinite cyclic subgroups, so F is isomorphic to direct sum of copies of additive group G. This means if F is pre-Abelian group, F is clearly denoted by here infinite cyclic subgroup, but this is infinite cyclic subgroups. So this means this is isomorphic to, by the theorism of the cyclic group, this is isomorphic to direct sum or direct sum of copies of additive group G. So every free Abelian group is isomorphic to copy of direct sum. Interesting statement is here, the statement. Let's read slowly. There exists a non-empty set X and the function eta x to f. This is little mishap. This denoted here looks like a hook. This is inclusion function. What is inclusion function? Every image is X itself, but contained in F. Then this here, yeah, eta. Then this is inclusion function, and inclusion function conventionally denoted the symbol eta. This and following property, if given an abelian group G is given and the function fx2g is given, so everything is this suppose this condition is satisfied, then there we can define or we can find unique homomorphism f2g such that here this statement is difficult and very complex, but later I will illustrate this statement with picture or diagram. Then this statement is will clarify. But this just statement text is so boring. Anyway, if we called F is pre-abelian group, because this is taking a following equivalent. Anyway, F is called pre-abelian group. Of course, each statement requires proof, but because of lack of time, we skip the proof of this statement. Okay, so for example, G direct sum G, let this is F, then this is pre-abelian group. Why? This is this statement is later, okay, because of we can clarify this is pre-abelian group by statement D, but we will restate and restate the statement D. So later we can see why this is pre-abelian group. But important thing is compared to pre-R module, the statement is following or statement equivalent is structure of the following statement equivalent is same here. So first we can say F is pre-R module if F is non-empty basis. B, F is direct sum of family of cyclic R modules. The similarity of statement is clearly revealed. So this means F is denoted family of cyclic R module. In this case, F is pre-R module, so R, F, go to the F, and F is satisfied R module condition, then F is denoted here. And by the statement C, this is isomorphic to direct sum of copies of left R module R. In this case, direct copies of additive group of G. In this case, copies of left R module R. And statement D is same, similar structure. Non-empty set X, non-empty set X, and this inclusion function is given. Inclusion function is given. Then there exists unique R module homomorphism. Earlier we defined the R module homomorphism such that here this is unique homomorphism such that this statement satisfies. Let's discuss about the statement D, which is one of the following equivalent condition of the free abelian group. The statement is complex, but by utilizing the diagram, we can understand easier and easier to remember the statement D. So statement D is here, the set X and the inclusion function and group G is, and the function is fxg is well defined. Then our aim is to find the homomorphic function, homomorphism by f. Even though you use any trick, we can find the homomorphic function, homomorphism find such that this relation, so find the homomorphism and this condition is satisfied, then F is pre-abelian group. But this diagram describes the relation is most surely described. Why? The relation is here. First, eta and composition F. This describe the relation. The arrow, many textbook arrow, express this arrow turn right here. This map goes to X to G. So this is same as here. For this reason, the diagram describes the statement of D. The most important, the good merit is this diagram is very succinct and concise. So we can remember this statement D more concisely. And if we find the example of free abelian group, we can utilize this diagram. For example, before we mentioned FG direct sum G is pre-abelian group. By using this diagram, we can catch this set is pre-abelian group. Why? Okay. Using this diagram, let's use this diagram. First, the set X. What is the set X? The set X is according to previous theorism, non-empty basis, correspond non-empty basis. So correspond the set X is basis, this standard basis 1 0 and 0 1. Set this setting and let G is integer. This is Abelian group is okay, and this is inclusion function. Satisfy this condition. So if we choose the element x, this not good, bad. This because the x is the set. So choose the U. Okay. Every element in F is consist because of the set. Because of this set is direct sum. This is consist A1, E1, where this for convenience this denoted E1, this denoted E2, plus A2, E2. Okay, and of course, because of this function is well defined, the value F1E1 and Fe2 is obviously well defined. In this situation, we can find the homomorphism function by F. The answer is here. If they choose element in F, this means A1, E1, A2, E2. Of course, A1, A2 is integer element. If we define this function is A1, Fe1, A2, Fe2. I already mentioned Fe1, Fe2 is well defined because of F is well defined. Then this map is homomorphism, satisfies homomorphism. This first condition is checked. To check the homomorphism, if we choose two elements U and V in F, the V in F, we can denote it B1 plus E1, B1, B2, E2. So the condition is here. F U plus V is F U bar Fu bar Fv. By the definition of the function f bar f, we induced directly easily check this equation. And to check the second condition is here. This means two functions are same. This means to check the second property, we check both f and eta is same as fx for all x in x. But because the element in x is only two elements, x consists of two elements, we can directly check f bar f eta e1 is same as fe1 or ei fei for all I is the index 1 and 2. So therefore the F is pre-Abelian group. Now we can see this commutative diagram again. This commutative diagram means this is here. Composition relation. If we find the homeomorphism or R module homomorphism function, then this relation satisfied. So this relation by understanding the commutative diagram, and according to the relation statement B, in fact B over C or over C, every pre-Abelian group or pre-module is direct sum of integer or direct sum of R module. It's the R. Okay, R mod, not R module, R. Okay. Then I want to say this commutative diagram can be generalization. This is pre-Abelian group. This pre-R module. Then is here. So if group R module, this come pre blah blah blah, we can generate this pre blah blah blah. So elsewhere group or R module, anything come this blah, if the conditional satisfy, then this is pre-object. So we can often say the here and here grossly pre-object. More concretely, a type of pre-object. To understand this concept, next lecture is category theorism. In category theorism, this property defined to find homomorphism or R module homomorphism, and this morphism is called universal property. Next lecture will concretely, more specifically, this theorism by using category theorism. And this mathematics, this field to using arrow or commutative relation. For example, even though this relation we can see here, we're familiar. If we linear algebra, we can see familiar this diagram, or this diagram is also familiar if we studied harder. Then this here the concept to deal with the this commutative diagram is classified as homology algebra. So, but next lecture, does not concentrate the homology algebra rather than pre-object and universal property and the definition of category. So next lecture, I will deal with this concept.